Hello everyone, welcome to BADM A724 Quantitative Methods and Business Analytics. This is lecture 6. I'm Dr. Frank Tianshi, your instructor for this class. In this lecture, we're going to cover discrete distributions, uniform distribution, Bernoulli distribution, binomial distribution, and Poisson distribution, and their applications. Okay. First, discrete distributions. Before that, let's talk about the random variables. Okay. What is random variable? A random variable is a function or rule that assigns a numerical value to each outcome in the sample space of a random experiment. Okay. We use capital letters to represent random variables. For example, capital X and capital Y. And we use lowercase letters to represent the values of the random variables, like undercase, lowercase x, lowercase y, etc. Okay? And the discrete random variable has a countable number of distinct values. Is discrete. The number of values is countable. So there are only certain numbers. Okay? For probability distribution, in case of the discrete probability distribution, a discrete probability distribution assigns the probability to each value of a discrete random variable x. To be a valid probability, each probability must be between 0 and 1. As we have studied before, that's the definition of probability. And when the probability is 0, this event is not going to occur. When it's 1, it's definitely going to occur. Okay? And the sum of all probabilities for the values of x must be equal to unity, as you know. That's all the possible possibilities together must be unity or 1. Okay. Let's take example of discrete distributions, coin flipping. Let's say you flip a coin. Okay, when you flip a coin 3 times, what will be the sample space? The sample space will has 8 equally likely simple events. Right? You could have what? You could have the head, tail, or tail, head, etc. Let's list all of them. Like this: the first toss, second toss, and third toss. Okay, and you do that, this is what you get. Right? You can have all heads, 2 heads and tail, head, tail, head, head, tail, tail, head, tail, 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 head, and tail, tail. Right? That's all possible outcomes you can have if you toss a coin, flip a coin 3 times. Okay. Now, what are the probabilities? Right? If you look at this, if we define the number of heads, right? In this case, how many for the first toss? What in this case here? What's the chance of getting a head? In this case you get 3 heads, right? In this case you get 2 heads. You do this, you get 2 heads, 1 head, 2 heads here, 1 head here, and 1 head here. Right. So what's your chance of getting 3 heads? There's 1 in 8 of them. Right. So the chance of getting 3 heads is 1 in 8. H. Same case with the tails, 3 tails. That is, you can also get 1/8. If x is the number of heads, then x is a random variable, because its probability distribution is as follows. Okay? And if x is the number of heads, so when you have 3 tails, x is 0, right? No heads, all tails, right? If you have HTT, THT, and TTH, they all have just 1 head, right? 1 head here, 1 head here, 1 head here. But you have 3 chances of that. So 3 out of 8, that's 3/8. Right? So if x is 2, the number is 2, you have 3 8s. The number is 3, you also have 1/8 of chance. So that's all the possibilities. If you add all these up, it's 1, because that's all the possible outcomes. Okay? Now, if you put them on our bar chart like this, remember histogram or bar chart like this? This is the number of heads. Could be 0, 1, 2, or 3. Right? And the probability could be this, or higher, 1/8, 3/8, 3/8, and 1/8. Right? So then you have a discrete distribution. Note that the value of x need not be equally likely. However, they must sum to unity. Okay? That's a discrete distribution, a coin flipping. And also note that the discrete probability distribution is defined only at specific points on the x-axis, only certain points. Okay? Expected value. Yeah. What is expected value? Right? And the expected value, or EX, of a discrete random variable is the sum of all the x values weighted by their respective probabilities. Okay? It sounds awkward. Basically, this is a better explanation. The expected value of x of this random variable, right, equals mu. Remember what mu is? We talked about this before. Is actually the mean, the average, right? The population. And let's put that aside for now. That expected value is xi times multiplied by its probability and then summed. And that is actually the expected value. If there are n distinct values of x, this is what you get, the expected value. Okay? And this is a measure of central tendency. Okay? If you think about the mean value, the average, the equation for the average, for the mean that we used before, how is that different from this? For the population mean, remember, mu for population is x summed divided by total number of n, right? And how is that different from this one? It's actually the same thing. Remember? In that case, when we calculate the simple means, mu, we add up all the xi's and divide by total number of n. Right? And each one of these values of xi has equal chance of being chosen. And each chance of that is 1 over n. So each one of them has a probability of p of 1 over n. And then you can move 1 over n out of this, and then it's exactly the same as your equation for calculating the mean. You do not follow what I'm saying here. I want you to go back to a previous lecture or book and find that equation and think through this. Okay? That'll be good learning opportunity for you. Now let's take an example here. The probability distribution of emergency service call on Sunday by Ace Appliance Repair Shop is this. Right? This appliance repair shop, like a Maytag repairman, for example, and they could get no calls. On Sunday, nobody calls, right? That chance, they figured, is 0.05. They could get 1 call. The chance is 0.1. 2 calls, 0.3. 3 calls, 0.25. 4.2. They could get 5 calls too, 0.1. And they never got more than 5 calls on a Sunday. Okay, that's add all this together is 1.0. Okay, what would you say the most likely number of calls they receive on Sunday? If you look at the individual probability, 2, you got 0.3, 3, you got 2.25. These two are the largest. You probably are trying to figure out or guess or speculate that the average number, most likely number, is probably somewhere between 2 and 3. If you think like that, you are correct, right? But we can calculate the expected value. So what is the average or expected number of service calls? Right? We can use the equation, right? We can use the equation, service calls equals xi minus pxi and summed, right? And we have x here, 0, 2, 5. Probability, right, given also x times px will be this times that, get you this, this times that, give you this, etc. Do the same thing, and then you add all these together, x, px together, added together. That's exactly what this is about. Sum up the big sigma is the sum of all here, the product of the two. Add all this up, you got 2.75. Remember we said it's the probability between 2 and 3? That's exactly right, 2.75. That's the average or expected number of service costs at this home appliance store. Okay? And you can also plot the service cost, the number of costs, 0, 1, 2, 3, 4, 5, right? And here the column heights of column represent their probability, right? So the expected value is right here. It's between 2 and 3 is 2.75, right? This point here, 2.75, and the mean is still, that's the balancing point or fulcrum of the chart. We call the fulcrum of the chart. It's the balancing point. Okay? Because EX is an average, it does not have to be an observable point, because you can't really have 2.75 calls, right? You can either have 2 calls or 3 calls, right? But here it's just an average. Okay? Variance and standard deviation of distributed distributions. Now, how do you calculate? Remember the variance, standard deviation, and how do you calculate that for a discrete distribution? If there are n distinct values of x, then the variance of a discrete random variable is this. Variance, remember, sigma squared is x minus mu squared times its probability and summed. Okay, the variance is the weighted average of dispersion of what mean, and it's denoted as the sigma squared. Okay, the standard deviation, of course, is the square root of variance, or is the square root of Vx, the variance right here. Okay. Let's take another example to give you a better idea. Yeah, you know the bed and breakfast, right? Those small, almost home, you know, like home run, home-based restaurant. I mean, hotel. You know, there's one single family house and many bedrooms. You know. And then the owners cook breakfasts for you, and you probably eat them with them. You know, because bed and breakfast. You have a bed and you have breakfast. And this Bay Street Inn is a 7-room bed and breakfast in Santa Teresa, California. Right? The probability distribution of room rentals during February is like this. The chance of no room, they have 7 rooms in this little family, home style hotel. 7 rooms, only 7 rooms. Chance of no room rented in February is 0.05. 1 room, 0.05. 2 rooms, 0.06. 3 rooms, 0.1, etc. Right? And total, of course, added up is 1.0. And most they can have all 7 rooms rented. Right? That's it. Okay. So, what is the chance, or what is the expected value? What's the average number of rooms? Right? If you look at the numbers probability here, you can see where do you see the most often? It's right around here, right? It's 0.13, 2.2, 0.15 here. So somewhere around here, you find the highest of a number. Their business is pretty good, right? They have either 5 to 7 rooms rented. So, to find the expected value, x times px and summed, right? X is here, px here. You multiply that, you get this, and then you add them up, the 4.71. So it's almost 5 rooms, expected value. So they expect in February they almost always have about 5 rooms rented. It's pretty good. Okay? It's like 4.71 rooms. And what's the variance then? The variance is x minus mu squared times px. Right? You have px, you have x times px. X minus mu squared will be x, this x 0 minus mu 4.71, and squared you get 22.18. For this one, 1 minus 4.71 squared, you get this. You do the same for all of them, right? And you add them all up together. Okay? And then you square them, and you square this times the probability, you get this, and add them up, you get secant squared. That's your variance, 4.22. Okay? What about there's 4.22 rooms squared, right? Remember, it's a squared term. Now what about standard deviation? We take the square root of that, 2.05. Okay? So the histogram, you can put it on the histogram that shows the distribution is skewed left and bimodal. Right here, this is the long tails on the left, so skewed left, and is bimodal. There's a peak of 5 to the peak of 7. Okay? The mode is 7 rooms rented, but the average is only 4.71 rentals. Right, it's a mode, and then this is average. Okay. PDF versus CDF. What is PDF versus CDF? PDF stands for probability distribution function. It's a mathematical function that shows the probability of each x value. CDF is a cumulative distribution function. It's a mathematical function that shows the cumulative sum of probabilities, adding from the smallest to the largest x values, gradually approaching unity. Just remember, just like what we did before, probability distribution function and cumulative frequency distribution. Okay? And this is PDF, probability distribution functions, like normal distribution. And this is CDF, is cumulative, as up, going up, all the way, approaching 1.0. Okay? That's illustrative histograms. Okay? The equation for these functions depend on the parameters of the distribution. Okay. Now let's talk about the uniform distribution. Characteristics of uniform distribution. What is uniform distribution? A uniform distribution describes a random variable with a finite number of integer values from A to B. Only 2 parameters here. Okay. Each value of the random variable is equally likely to occur. Let's consider the following summary of uniform distribution. Basically, this is all the equations here. Parameters A and B, upper limit, lower limit. Right? This is PDF. A and B is the limit. Right? And this is a range. This is the mean. This is standard deviation. And you're not expected to memorize this, but you just know how to find it, how to calculate that. This is for uniform distribution. Okay? Let's take an example of that. Yeah. Suppose you roll a die. Rolling of a die. The number of dots on the row of a die form a uniform random variable with 6 equally likely integer values. 1, 2, 3, 4, 5, 6, right? And what is the probability of rolling any of these here? Okay? Then we know that for all of them, the PDF is this, they're all equally likely to be shown on top. Right, so they all have the same height. They're PDF for one die. The CDF is the cumulative. You keep adding up until all of them, the 6. That's a 100% probability. 1.0 probability. The CDF. Okay. And so the PDF for this is 1 px 1 minus b minus a over b minus a plus 1. 6 minus 1 plus 1 is 6. 106. So the mean is, plug in numbers, get the mean, and the standard deviation is, plug in the number, you get 1.7. Very easy. Okay. Bernoulli experiment. What is Bernoulli experiment distribution? A Bernoulli distribution or Bernoulli experiment is a random experiment with only 2 outcomes. That's called a Bernoulli experiment. One outcome is arbitrarily labeled as a success, x equals 1. The other is a failure, x is 0. We use the pi. That's the p of success, probability of success. 1 minus p pi is the p failure, probability of failure. Okay. Of course, it has nothing to do with success or failure in life, in work. We just call it success. A success is usually defined as a less likely outcome, so that the pi is less than 0.5 for convenience. Okay. And P0 plus P1 equals 1 minus pi, plus pi. Remember, P1 is pi, and P0 is 1 minus pi, so that's 1. And pi is between 0 and 1. That's Bernoulli experiment, okay? With only two outcomes. So what will be the experimental two outcome? Like flipping a coin. It's the Bernoulli experiment. Okay? The expected value of Bernoulli experiment is x times px, right? Summed 0 times 1 minus pi. That's the probability of getting a 0, and probability of getting pi. You multiply it, you work this out, you get a pi. Very easy and straightforward and simple. The variance of Bernoulli experiment is this. You plug in the equation 0 and then pi, you get that. Okay? The mean and variance are useful in developing the next model. Okay? It's called the binomial distribution. What is binomial distribution? The binomial distribution arises when the Bernoulli experiment is repeated n times. You start with the Bernoulli experiment, remember, with two outcomes. You repeat it n times, you get a binomial distribution. Each Bernoulli trial is independent, so the probability of success pi remains constant on each trial. In the binomial experiment, we're interested in x number of success in n trials, so x equals n plus x1 plus x2 all the way to xn. Okay? The probability of a particular number of success is determined by the parameter n and pi. Okay? The mean of the binomial distribution is found by adding the means of each of the n Bernoulli independent events. You add up all the pi, since there are n of them, so it's n pi. The variance is that, okay? And the standard deviation is the square root of this, okay? And here the summary of all the binomial distributions. You don't have to memorize this, just know where to find it if you need to. Okay? I'll give you an example here so you can have a better understanding. Let's go to say you have a quick oil change shop, right? It's important to quick oil change shop to ensure that the car's service time is not considered late by the customer. And remember, there's one shop that says they're going to get your car oil changed in less than 30 minutes, or it is free. So you can't, and then in most cases you probably get it done in 30 minutes. Okay? So the service times are defined as either late or not late. Okay? If X is the number of cars that are late out of the total number of cars serviced, then it's a random variable, right? Because you never know how many cars will be late. So there are some assumptions though. Cars are independent of each other. Everyone is independent of each other. The probability of a late car is consistent. And we'll assume that. Okay? And then what is the probability that exactly 2 of the next 10 cars serviced are late? Or x equals 2. Let's remember the car is late, the probability is pi 0.1, right? So the probability the car is not late is 1 minus that is 0.9. Okay? So px, using this binomial distribution, we can calculate px equals 2. That's the probability that exactly 2 of the next 10 cars service are late is 10 factorial, n is 10, right? X is 2, n minus x, 10 minus 2 factorial, times pi to the x power, 0.1 to the second power, 1 minus 10 at 10 minus 8, 2's power, right? You carry out this calculation, you get a 0.1937. So what does that mean? That means the probability that exactly 2 of next 10 cars serviced are late is 19%. So, and that's pretty high, right? How about another application? Uninsured patients. We know that on average, 20% of emergency room patients at this hospital don't have insurance, health insurance, right? And in a random sample of 4 patients, what is the probability that at least 2 will be uninsured? If X number of uninsured patients success, well, it's kind of ironic to use called success, right? And then the probability of uninsured, or pi, equals what? 20%, right? 0.2%, 0.2 to 20%. Okay? And then the probability of insured is 1 minus that pi, that is 0.8. Okay? And then n is, in this case, 4 patients. Okay? And the range is 1, 2, 3, 4, 5, 0 to 4 patients, And what is the at least 2 will be uninsured? What is at least 2 will be uninsured? There'll be 2 or 3 or more uninsured, right? So individual probabilities can be added to obtain any desired given probability. For example, the probability that the sample of 4 patients will contain at least 2 uninsured patients is that. So what inequality means at least 2? It's larger than 2, it must be P2, plus P3, and P4, right? That is at least 2, okay? But then we use the equation we have for binomial. We can calculate P2 as 0.15, P3 0.02, P4 at 0.0016, a chance 0.1808. Now that is at least 2. So that's a chance. Next, for the sample of 4 patients, 18% chance that at least 2 will have no insurance. Now let's ask another question. What is the probability that fewer than 2 patients have insurance? What is fewer than 2? If there only 1 person having insurance, that's fewer than 2, that's P1. Well, nobody has insurance, that's P0. So that's fewer than 2, right? Fewer than 2, we calculate P0 and P1, and then we get 81.92%. That is the probability of fewer than 2 patients having insurance. Okay? Now, what is the probability that no more than 2 patients have insurance? What is normal than 2? Right? If normal than 2 is actually 0 plus 1 plus 2. Right? It's no more than 2. Right? You cannot have more than 2. Okay? If you put that in, you get 97.28%. So you can see that you can use different ways to calculate the probability for binomial distribution. Okay. What is the mean and standard deviation of this distribution? The mean is n times pi, 0.8. Standard deviation n times pi, 1 minus pi, multiplied, then square rooted, that's 0.8. Okay, straightforward. The next one is called Poisson distribution. It's also called the model of arrivals. Most Poisson distribution application model arrivals per unit of time. Like, for example, how many people are arriving at the train station in a given time. Right? The events occur randomly and independently over a continuum of time or space. Right? For example, this is flow time, right? And this is 1 unit of time, another 1 unit of time, and then another unit of time, and 1 unit of time. Right? Each dot is the occurrence of the event of interest. Right? So let's say x is the number of events per unit of time, and x is a random variable that depends on when the unit of time is observed. For example, we could get x equals 3, x equals 1, or x equals 5 events, depending on where the randomly chosen unit of time happens to fall. Okay? If it falls here, the unit falls here, you can see 3 people arriving. If it falls here, you can only 1 arriving. And here, you can find 5 people arriving. Okay? So it's random sample. And this is called following Poisson distribution. A Poisson process has only 1 parameter. Poisson model only has 1 parameter. That's called lambda. So Greek letter lambda. Lambda is the mean number of events per unit of time or space. Okay? The unit of time should be short enough that the mean arrival rate is not large, is less than 20. Then we can use the Poisson distribution. To make lambda smaller, convert to a smaller time unit, you can get a smaller lambda. Poisson distributions are always right skewed, but become less skewed and more bell-shaped as lambda increases. These are the equations for lambda Poisson distribution. Okay, that's the probability distribution function. The range, mean, and standard deviation, very simple, just square root of lambda. Mean is simply lambda. Okay? Let's take example here. Credit union customers. On Thursday morning between 9 a.m. and 10 a.m., customers arrive and enter the queue at the Oxnard University Credit Union at a mean rate of 1.7 customer per minute. As soon as you see this arrival at a certain rate, that's a Poisson distribution. Okay? Then from the PDF, we plug in lambda 1.7, x, and e lambda 1.7. This you get a PDF. Okay? And then mean of this lambda is 1.7 customer per minute. Standard deviation is square root of that, and is 1.3. Okay? Here is a Poisson probability distribution for lambda 1.7 customers per minute on average. Okay? You can see this number. This is the probability distribution for 1.7 customers per minute on average. Okay? And then there's a PDF, there's the CDF. Now the X represents the number of customers. Okay? For example, PX4 is the probability that there are exactly 4 customers in the bank. When the X is 4, there are 4 customers in the bank, that's the probability. Okay? When there are 2 customers in the bank, that's the probability. When there are 9 customers in the bank at the same time, it's a very small chance, 0.0001. Okay, that's from the PDF. We can make calculation of this. Okay? Now, this is for 4. Now let's ask a question. You can also calculate cumulative probabilities. It can be evaluated by summing individual X probabilities. Now let's ask a question. What is the probability that 2 or fewer customers will arrive in a given time? What is 2 or fewer? Right? 2 or fewer is either 0 or 1 or 2, right? All of these are 2 or fewer customers. So you find P0, P1, and P2 from the table we just saw, and you plug in the number, it's 0.75. So the probability of 2 or fewer customers will arrive in a given time is 75%. So that's pretty high. Now, what probability of at least 3 customers? The complementary effect. Right? If fewer than 2 is that, what about at least 3? That's complement of this one, right? So we can just go 1 minus that, 1 minus this, will give you 0.24. Okay? That's at least 3 customers.